I mean, we haven't, other than Adil's lecture, we haven't done a single lecture in PDEs. I guess I gave one on first order nonlinear PDEs, but it's all been this review chapter. So it might be a good idea to kind of look at possible directions, where we're going, that sort of thing. What I will start with is, well, let's see, I will start with kind of just discussing what functional analysis is from a non-rigorous perspective. The one sentence definition is infinite dimensional linear algebra, studying linear structures, linear spaces. So I won't write down the definition, the axioms, because I forget them, but we all know what a vector space is. So V is a vector space. I'm assuming we all know what a vector space is. Is there anyone who doesn't?
Well, let's just write the axioms. So vector space is a set with two binary operations, right?
Sure.
No, actually one, but just write, yeah, let's write what these operations are.
Yeah, let's say it's a set over a field.
Right, so this field can be, say, reals or
Complex numbers, right?
yeah,
With a binary operation defined.
called addition, right?
Addition from the vector space to itself, and another called multiplication. Let's say binary
Scalar
operations.
multiplication.
Right, scalar multiplication.
Well, that's the other one is not a binary operation. It's
Oh, sorry.
no, this was right. This was right. Yeah, right.
Yeah.
Okay.
And then a binary operation from the field in the vector space to the vector space.
Right, and we
Maybe
don't
that's-
call it a binary operation, strictly speaking. Okay.
Sure. And these have to satisfy that it's closed, of course.
Well, first of all, it's commutative, associative,
Right.
right?
So this is commutative, associative.
There is zero, there is identity. There is an opposite element, inverse with respect to identity.
Inverses.
Yeah.
So
And
it's just a commutative group over this.
yes. And then
Distribution.
distributable, right?
So and then if we have a scalar, if these two things are true, then we have the A.
Yeah, this is pretty much all, yeah.
Okay. And then we also have the zero scalar. I think this is an axiom.
Yeah,
It's not?
gives you zero, yes.
Okay. Well, it can be proven with the previous. So, okay. And this is our vector 0. So this is all of 254, 454, the idea of a vector space. When we have this idea, we have the notion of vectors that are linearly independent. So a set with each element from the vector space is called linearly independent if for all scalars not all of them being 0, sorry, linearly dependent, we can write
So this is for finitely many. Just write the sum from 1 to n, or to m, whatever. Yeah.
And then the idea would be we don't need to restrict this to finitely many vectors. And we can talk, therefore, about a basis where we have a set of linearly independent vectors that also spans the space. And then when we extend this idea and we say we can have infinitely large linearly independent sets. And of course, linearly independent means that this equation is not true for all scalars.
Well, you need to say what span is first.
Sure. So,
Or set. Well, it could be an infinite set, just
sure.
the span of any set is, doesn't even have to be countable, just any set. The span of a set is equal to all linear combinations of this.
Right. And then this is for all Cn in the field.
No.
So all linear combinations of these vectors give us the span of that set of vectors.
Well, finite. The n goes from 1 to
finite.
n. Well, for all n, yeah. For all capital N, yeah.
Right.
So what is the basis?
Right, and so a basis for a finite dimensional vector space. Just a set of vectors that is not linearly dependent, so linearly independent.
Just say linearly independent, yeah.
Say a set A where the span is equal to the vector space.
Right. So basis is a subset whose span is equal to the whole space. Okay.
Right.
And now what is the finite dimensional vector space?
Right, and so the dimension of A, or the dimension is just the cardinality of A, where A is any of these
So if
bases.
it is finite, then it's finite dimensional. If it's infinite, then
So then a vector space right? And so this is all we study in, well, except for one section, all we study in Math 454 and 254. This is most of the common examples we're used to. Rn, or all of them are in some sense isomorphic to Rn for a specific n, depending on exactly what this dimension is. And so functional analysis is everything that is the same up to this point, except for this restriction on dimension is not the same. We talk about infinite dimensional vector spaces. I don't think I remember concisely enough how we can then define, well,
how you define what?
well, the different kinds of basis and that sort of thing. He doesn't talk about it at all in this review.
What do you mean different kind of? What would be
Well,
kind?
a Schroeder versus a Holder basis and that sort of thing. Just the different ways of defining a basis.
You don't need to do it now.
Okay. So what he then discusses is all of this, this theory that we have here is just for a vector space. We can define additional structure on this to define normed and inner product spaces. And these are the objects we study in functional analysis. And specifically in the applications to PDEs, we almost always need a norm, we almost always need some way of discussing length, of discussing the size of our vectors.
So why don't you give examples of infinite dimensional vector
Sure.
spaces without any norm, without anything?
Sure. So we can discuss, well, we can just discuss sequence spaces, right? So the sequence space is the set of sequences these have infinitely many components.
Like, are these complex or,
It doesn't
for
matter.
example, complex?
Sure, right, from any field where each of these is just, say, a complex number.
And the scalars are also complex from the same field, right?
Right. The vectors here would be each, one way you could think of a basis for this would be the set of vectors with a 1 in each component.
So you need to define addition of vectors and multiplication by scalars, and then you'll see that it satisfies all the axioms, right? So
Right.
basically that's one. What else? Like functions.
Right, so our function space, we could have the continuous functions. Well, let me see if I can think of an easy way of describing that.
Well, why don't you just say all continuous functions in the interval 0, 1? I mean, that's,
Sure.
you could just say words, yeah.
Right, all functions from 0, 1 to, say, r, such that they are continuous.
Why is that a vector space?
So we can define scalar multiplication just by multiplication by real numbers. And we can define addition by just addition of the functions.
And so if you add two continuous functions, it remains continuous, that's why it's a vector space.
Right.
And you could do C infinity and things like that. It's all,
Right, and so we could just put a k here, and I think we've talked about this space in the seminar, and this is where,
Fk is continuous. Okay.